Hi, and welcome back to HL bonding. This time we're going to revisit the idea of sigma and pi just to give you a bit of a refresher. We've seen sigma and pi bonds and those ideas already when we did HL organic, and we sort of stole a little bit from HL bonding when we did that. So just a quick refresher on those types of bonds for you. So as we've said, with a covalent bond, we have the electrostatic attraction between a pair of electrons, a shared pair of electrons, and the two nuclei involved in the bond. Okay, so essentially there must be a region of electron density between the two atoms where they're shared. We know from atomic theory that the electrons exist in atomic orbitals that are regions of space around the nucleus of the atom. So depending on where the outermost shell number is, because we know that this sharing occurs with valence electrons only. The valence bond theory then links these orbitals and bonding and describes how orbitals can join to form chemical bonds, i.e. the overlap of two orbitals to form a bond. When we have the overlap of these orbitals, we get what we call molecular orbitals. And very shortly, in our next couple of videos, we'll be looking at how these orbitals change shape and the idea of hybridization, how we get, with the new molecular orbital, a different shape and different energy level than the two orbitals were before they bonded. But the two orbitals from the different atoms, each containing a non-bonding paired electron, merge in the region of space between the two atoms. Okay, so they're merging in this gap between the two nuclei. Okay, so the sharing of electrons in a covalent bond acts as a result of the interaction of overlapping of a half-filled atomic orbital from one atom and the half-filled atomic orbital from another. When this is hydrogen, we have the 1s1 orbital overlapping usually with a 3p5 in the chlorine or something, 3p3 from the carbon, something like this. Okay, remembering these relate to our electron configurations, 1s1 being hydrogens and then 1s2 to s2 across, and then 3s2 and 3p5 for chlorine. So this is just referring to the highest energy occupied orbital in the chlorine atom. Okay, so both these single and unpaired electrons now become paired as they share each other's overlapping atomic orbitals. Okay, so which orbitals overlap and how dictates whether we call it a sigma or a pi bond. Hopefully this will all seem very familiar. So sigma bonds are always formed from the end-to-end overlap of either two s orbitals, remembering s orbitals have our spherical shape, s for sphere, or an s and a p. So we can have this s and s orbital forming the new molecular orbital, okay, an s and a p forming the new occupied molecular orbital and an unoccupied molecular orbital, or the end-to-end or head-to-head overlap of two p orbitals. Okay, so we would have the end-to-end of these two p orbitals here. So S and P are going to be basically hydrogen and anything else. Two P's are going to be where we see the single sigma bond forming between any halogens, and of course two S's are always going to be in that H2 molecule. What this does is the molecular orbital is formed along the internuclei axis. Okay, so they're most likely to be found along the axis that is between both nuclei, the internuclei axis. Pi bonds are the sideways overlap. That is, we have two p orbitals, we can see from this shape here, the bilobed p orbital. And what we have is these are usually py or pz, remembering that these form along an XYZ plane. Okay, so we have a lengthwise overlap, not end to end, between two p orbitals. This will occur when the atoms come close together. So a sigma bond has already formed from the overlap, the end to end. the end-to-end overlap here. And when this forms, it pulls these atoms closer together and allows the sideways overlap to occur between these py orbitals here. Okay, so once we get that sideways overlap, we now create a larger new molecular orbital cloud where the electrons can, and we get our double and triple bonds forming, always from the sideways overlap. So when we have a double bond formed by 1 sigma and 1 pi, a triple bond will be formed by 1 sigma and 2 pi. The pi bonds are weaker due to the sideways overlap. The end-to-end overlap is a stronger and shorter interaction. Okay, so the double bond is less strong. It will be more reactive. That bond is easier to break, so it will be more reactive. Okay, so pi bonds are weaker than sigma bonds. A double bond will be less than twice the strength of a single, and a triple bond is less than 3 times the strength. And we can see these differences in strengths by looking at the bond enthalpy for a single, double, or triple bond. When we have a single bond, we have 1 bond enthalpy. When we have a double bond, it is not twice the enthalpy of a single, and a triple is not 3 times. Okay, and this is because those pi bonds are weaker. Okay, so just reiterating this, a single covalent bond will have 1 single bond, which is the end-to-end overlap of either 2 s orbitals, or an s and a p, or the end-to-end of 2 p's. Oops, got my p orbital shape wrong. Okay, so the 2 p orbitals, there we go. Pi bonds are always formed by the sideways overlap. Okay, sideways overlap of p orbitals, and we will have a 1 sigma and 1 pi for a double, and a 1 sigma and 2 pi for a triple. And that's that. Next up, we'll be looking at molecular orbital hybridization and formal charge.